is communication.
Oh, Mr. Donut, I presume.
Yes, I feel thank you that I'm here to welcome you, Mr. Larsson.
You should be. Has to be very spontaneous. Okay, we're two seasoned software engineers discussing code as communication. In this podcast, we will be talking about what makes code high quality, and that is communicating the intent to the other team members or other stakeholders.
Yes, and in this episode, we're talking about knowing your programming language. How is that important to be able to communicate?
Yes.
And of course, you have to know the basics, but some people write their code with like simple tools that every language provides instead of using the more intricate language features and the more idiomatic way to express your intent.
Yeah, and I think this is extra relevant for Python, where there are at least two very clear groups of users. So you have the software engineers on one side, and on the other hand, you have another group that just uses it as a script language. So I think we have quite a few examples from the Python world.
Well, from a Python word, I have one example. From the C++ word, I have two. So do you want to start out with an example?
Yes, so maybe I should start with Java examples. And I would say that in general, even seasoned developers tend to be lazy. They will write code that works fine for their test examples, but in the real world, they quite often run into scaling issues. Where the code that works perfectly well for small sample sizes will just not work at all on a real world example. And I think one common example is streams. They're very handy to deal with collections, etc., in a unified way, and it's very convenient to write functional code in Java. As in the functional paradigm. The problem is a bit that when you run into tight loops over larger data objects, such as matrices, where you have a few thousand rows and columns, streams will not provide the necessary performance. Instead, you need to go back to the standard for loop. Because the stream doesn't really work in that larger scale.
That's interesting because actually, when you think about it, an API like Streams would provide more information to the compiler than a generic approach with for loops.
Yeah. And that is like the standard view that most people take. Most people just use streams for everything. But when you need tight loops with performance-sensitive operations, then you simply need to go with old for loops.
Is the old thinking for Java not to use string operations still valid? Or is string operations now not slow as hell anymore?
Yeah, there are a lot of workarounds for string manipulation, so it's less of an issue now. But you should be aware of what you're doing with strings, of course.
Yeah, so when you just naively use like string concatenation and stuff like that, it's still slow, is it?
It is, but the thing is, that's been around forever, but string buffer, etc. I will deal with this for you, so it's quite easy to get around.
Yes, but you have to be aware of that. That's, I think, the big theme of this episode. We want people to be aware of what the language can do and where are the weak points.
Yeah. In this particular case, I think anyone that has taken a master in computer science will be aware of this, and it would be an important topic, whereas it might be less common among people going to, let's say, boot camps or being total autodidacts.
I wouldn't be so sure that master of computer science know more in that area. I mean, one of the best programmers I've ever met actually mastered, well, it was diploma, because back then German universities didn't have master in biology.
No, I see there, but I would consider those guys, maybe the best programmers really are the ones self-taught without a degree, but I'm talking about in general. if you compare the average computer science master to the autodidact. But maybe I'm just assuming.
I don't know. I don't have any statistics about that. It's just
No.
like when I compare the people that I've met in real life up to now, I wouldn't bet too much on university education. I mean, there's value in it because you get a solid theoretical foundation, but you don't necessarily get too much knowledge about how the connection to the hardware is, where limitations are, etc.
Yeah, okay. I see your point, yes. I would like to mention that a common area of misconceptions or where you have performance issues again would be the Java virtual machine. Depending on your level of understanding of the Java virtual machine, you will have very different outcomes when it comes to optimizing your code or structuring it properly for performance. I mean, there's quite a few even really seasoned software developers where they have no clue about the virtual machine and garbage collection, for instance.
Yeah.
But this is, again, I mean, optimization in itself is really a bit of a murky subject because it's mostly relevant for highly specific fields like high-frequency trading, etc.
I don't think it's irrelevant for other areas as well. So even when performance is not your issue, it's still a question of how much you have to invest in hardware, in energy, etc.
Yeah.
So even in those cases, you should think about it.
That's true, yes. But too often you see the backside of optimization, then that it's the topic of prematurely optimizing, where you optimize well before it's really relevant, and then you miss out on what you actually want to achieve with your project.
Yeah, that's true.
Might do that.
That's true. And actually, I think the saying about premature optimization is the root of all evil has a lot to do with the way people do optimizations when they do them prematurely, because they often do it based on beliefs and not based on actual measurements. When I was in a really high performance project, we figured out that we would have to measure everything. So I actually wrote a performance testing framework, which would shield the CPU core, bind to it so that nothing else could interfere. And then it would use the tick count register to really fine-grained measure the performance with several loops of heating up, and you had a graph and set, etc. Measurement is the more important part. It's not about so much, I think, when you do that optimization. It's more about whether you
make the right optimization.
Exactly.
On the topic of optimization, I would also say that there is some of a trade-off between maintainability and super optimized code.
It
might be. It's not necessarily true for all the
It might be, but actually my experience is that most of the time, when your code is easier to read, it's also more performant. It's not always. There are a few things, but in general, all those tricks that people still teach each other, most of them make things worse because they don't tell the compiler what you're trying to achieve, but try to tell the compiler how it is supposed to do it. And the compiler usually knows more about your CPU architecture than you do.
I hope so.
So a typical thing that you hear in C projects is using shift operator instead of multiplications. You really think your compiler doesn't know that trick and doesn't know when it's better or not?
I think this is also related to a bit how up to date you are on compilers, etc. Because if you started out in the 70s or 80s, shift operations would make sense, of course. But today, as you say, it shouldn't be the case.
In a C++ project, also very performance bound, actually the same one that I talked about before, we had this discussion about exceptions. And there were some people who said, exceptions are just too slow, we cannot use them. Well, the alternative is to return an error code. Now, if you do that on multiple levels through your call stack, then in every step, you have to check the return code. That's an if statement.
And it's costly then, yes.
Well, if you do it just on one level, it's faster than throwing and catching an exception. I did the measurements back then. It was like 3 or 4 levels of function deep. Then the exception gets more performant.
Yeah.
Now, that doesn't mean...
And I would also say that the general way to deal with exceptions is that they should really be an exception. It shouldn't be a way to handle normal program flow.
Yes.
Which, you tend to discover such examples in reality, unfortunately.
Yes, yes.
Yeah.
So exception is I cannot handle what I am supposed to do. Like, for example, I'm supposed to send a package over the network, but the connection is broken.
Yeah.
It comes a bit back to what we were talking about last time there as well. You want to have an API that is easy to use on the caller side. When you have a function that sends a package on the network, you want to not have a return value because it doesn't make sense to say my variable equals send, because sending is just one directional. If you read, you want to have the buffer as your return value.
Yeah.
In those cases, if things go wrong because the connection is gone or whatever, throw an exception, because then you have a better API for the user of your functions.
Yeah, I would agree, yes.
And I think that automatically leads to using exceptions for really things that are errors. If you have this kind of rules, like if I cannot handle what I'm supposed to do, then that's an exception. If I can handle it, maybe differently, maybe with a workaround, it's not an exception.
Yeah. No, we agree on that, yes.
We so rarely agree. On the other hand, if you look at languages like C# or Java or Python, there an exception actually collects all the stack trace data.
Yes.
So these rule of thumb that I said, C++ exceptions are not that bad. When you throw them through multiple levels, they are faster than return value testing. That doesn't translate to every language.
No.
On the other hand, you want to have exceptions when things go wrong, and then you don't care about performance anymore so much. So
I guess this is a good time to arc back a bit to what we're really talking about. That is knowing your language.
Yes.
And in this case, is really knowing how it handles exceptions and
exactly
what is more performant
exactly
in your use case.
Yeah. Okay, so for example, in C++, modern C++ has several ways of doing compile time programming. And since you usually use C++ in an environment where you want to have high performance, because why would you bother with C++ otherwise? Use them. There's like const expr, const eval, know the difference. Const eval is always evaluated constant, and if you pass in something that is not constant, not known at compile time, it will break. And const expr will fall back to dynamic evaluation if you pass in something that is not known at compile time. So those are behave different. You can use templates. They are useful. In modern C++, less so. We used to do a lot of things with templates that you can solve with const expr and const eval nowadays.
Yeah.
That's one of the things with premature optimization. I mean, things that the compiler can calculate in compile time don't take time at runtime. So those are optimizations that if they can be applied, if it can be calculated at compile time, drop them in, use them.
Yeah. I would agree. I mean, I'm not really up to speed on C++, but the way I interact with it is really when I translate some old C++ project into Java, for instance. And it's you still lack quite of the convenience of C++. Apparent when you work with a larger code base.
Yeah, what I've seen a lot is people that have worked a lot with Java moving into C++, and then they take their idioms.
Exactly, I would agree, yes.
And that's, I think, a big issue. For example, in Java, it's pretty common to have open and close functions for stuff like files or so. in C++, you would use the constructor and the destructor for that.
Yeah.
Because then you can be sure that the close is actually executed when the object goes out of scope.
Yeah, but this is less of an issue with later iterations of the Java language, because now you have the let's
You
cut there.
mean the try block with
Exactly.
Yeah, but it's still different because the way people think when they design a Java API makes a lot of sense in that environment of Java.
Yeah.
But it doesn't make sense in the environment of C++ because how people expect C++ code to be written.
No, I just wanted to mention that you have this try with resources concept now in Java.
Yeah.
But I think your point is still valid. Yes.
Yeah, it's not so much about that there is resource allocation is initialization in C++. It's more about that's how you do it idiomatically in C++. In all languages, like know the idioms. In C++ you have that kind of idiom, how you build things. In Java you have a different idiom. None of them is worse or better, but if you read C++ code, you expect C++ idioms. Another example where I've seen that pretty often is Python classes with a lot of getters and setters written by Java programmers, Of course. Now, it makes a lot of sense in Java, but in Python it doesn't.
True. And actually, I think that there's also this habit of using annotations in Java where you handle all getting and setting via just an annotation, like at data, for instance, and then you don't have to deal with it yourself.
Yeah.
And then that question is how that translates into Python, for instance.
Yeah, in Python you would use a decorator called...
like a property decorator.
Yes, exactly. It looks similar, but it's very different to how that works in Java. So you have to, again, know how your programming language works, how it does the things that you're trying to do, and use it idiomatically.
Yeah.
Another thing from modern C++, ranges library. It makes things so much easier to read because you have like your collection. It's similar to the streams library in Java. So collection, pipe, take file. You have a new collection or a new range in C++. It's called range because it doesn't contain anything. Actually, it's a view on the data. But you have a new range that just you can just iterate over the first 5 elements of it, or you can transform stuff. So you iterate over the transformed data and stuff like that. And it's really just says very explicitly what you're trying to achieve. It promotes what I call programming in expressions. Programming in expressions is part of what you would consider functional programming. The ideal programming in expressions is a return statement with an expression.
Yeah.
I mean, that can be overdone, but features like ranges library in C++ or comprehensions in Python, they make exactly that easier and make it more natural. Now, why is that a good thing? It's a good thing because you're again writing down what you intend and not how you expect the computer to execute it. So that's the big difference between thinking in functional programming or thinking in imperative programming. In functional, you say what you want the computer to do, and in imperative programming, you say how you want the computer to do it.
Exactly.
Also other features like lambdas, coroutines. I mean, coroutines are pretty new in C++, and they don't have the necessary library support yet. But as soon as that is available, use it, use lambdas. I mean, don't use them everywhere like being forced to it, but know about them, what they give you, and then use them where they improve the expressiveness of your code.
Yes. And I think this highlights another very important point in knowing your language. It's also updating your knowledge of the language, keeping up to date with changes, etc., and being able to filter out what's only a fad or a trend and what's really important and what will really help you.
Mm-hmm. Yeah. Sometimes you will follow trends. It's not that it's like a hard rule there, but because I've been working with XML and XSL when it was hot.
Yeah.
Not that I thought it's the best thing ever, but it was like, okay, that's how we do this nowadays.
Yeah.
And I don't think that's a necessarily terrible thing. But on the other hand, there's also this JavaScript illness of having a new framework every week or so.
Yeah, I think their entire infrastructure needs to be reconsidered or reworked a bit, because if you look at, for instance, how you deal with NPM and the package handling in JavaScript and Node, for instance, it's a bit of a mess, and people just tend to add dependencies where they're not needed, and in the end you have just a huge mess.
Mm-hmm.
And you have too much code being downloaded for it to be really efficient for what you're actually trying to achieve.
Yeah, it's also a part of knowing your language, because that includes knowing your environment where your code will run in.
Yeah.
So when I write JavaScript code, it's usually client-side.
Yeah.
So I have to know that the browser has to download the code first before it can even execute it. So I have to make sure that I don't include stuff that I don't need.
Yes, ideally this would be the case, but I think a lot of people skip this part and just add whatever to make it work.
Yeah, I understand that, because, I mean, making it work is kind of important. So,
yeah.
But on the other hand, it has to work, but just working doesn't make the code good.
Exactly. In the end, I think you might run into a lot of maintainability issues if you just make it work. You have to spend some time thinking about, even if you're under time pressure, just spend some time thinking about how this will work in the future, or if there are any changes to, let's say, your dependencies.
Exactly. And making it work is like the AI can do that, but it's not communicating.
Yeah. Which is the most important part.
Sometimes the AI can't do that, but yeah.
Yeah.
I have one that I've hinted a bit to, and that's the comprehensions in Python.
Oh, yes, yes.
When I use them, I often hear that's so difficult to read. It's not. It's basically a for loop with an if statement, and that's what you write down.
Yeah. I think this goes back a bit to what we said in the beginning about different user groups for Python. You see the ones who are actual programmers and those who use it as a scripting language, just translating what they're doing in mathematics or statistics into a programming environment.
Yes, but what are those people doing in an environment where they are writing like real applications?
That's a good question, but it's more prevalent than you think.
I know, we both know. I think there's even more groups like those that you've described, but for example, also people who do mostly data science. They like to use Python as well because it's easy to learn for the first few steps, but then they stay there. And I get it. They're not interested in learning a programming language. They're interested in analyzing data. I think if people like that work on a real big application, they should have people who know programming, and they should be in the team, and they will come up with a math part or with a data science part, and then the people can collaborate and still create good code using the features of the language.
Yeah. I would also like to highlight in this case that if you're a computer scientist, you should also be able to handle data science and all the aspects of it. It's not that super...
Data science can be a bit more than most computer scientists are able to handle. So there's a lot of statistics in there and stuff like that. So I wouldn't say that generally. I mean, it's like with the people that you were talking about. They usually know a lot about the math part they are involved in.
Yes.
But they should collaborate with people on their team that know programming, because, you know, when I have a plumbing issue here, I can tell the plumber where the leak is, but he can fix it better than I can. So why not tell him here's the leak and he can go there and fix it, instead of saying, only I know where the leak is and that's why I have to fix it myself as well. And then break things.
And again, this is another example why code is communication. You should really communicate about
Yes, exactly.
in order to achieve the best outcome for the entire ecosystem.
Yeah, actually, the comprehensions, especially when you come to data science, those are important because in Python, comprehensions actually are faster than their for loop alternatives. Let's say you create a list comprehension. And then what you write down is, I want a list with this content. And if the interpreter has a way to find out how much memory this content needs, it can allocate it upfront. It can make sure that the elements are allocated in the same memory block and lined up after each other and stuff like that. And that's a pretty significant performance difference. Compared to when you do it with a for loop, you create an empty loop. The interpreter knows, okay, I create an empty loop. No memory. Then you run through your for loop and you say, please append this to my list. Okay, the compiler appends it. But there's no place where you tell not the compiler, the interpreter, where you tell the interpreter that you actually want this as the result. So it has at least a very hard time to optimize for it. Comprehensions allow the interpreter to optimize that part. Now, Python is not the language that you use for performance critical stuff. But even there, as we said before, in every project, you want to not unnecessarily make your code slower than it has to be.
So a question, would you consider, if you think about a novice programmer and a senior programmer, do you think the difference is bigger in Python than in Java or C++ in terms of the outcome? Because I feel like in Java, even if you do everything wrong, it's still pretty performant. But in Python, it could be disastrous.
Well, it could be disastrous in Java as well.
Yeah.
Maybe not that disastrous, but you can pretty much break your performance in C++ with wrong decisions as well. So
that's true.
I think Python has a very low entry barrier. And
Yes.
its biggest issue is to get people to continue learning.
Agree.
Whereas, for example, on the other end of the spectrum, C++ has a very high entry barrier. So you already have maybe not huge, but quite some knowledge before you actually want to use that language.
Yeah, and I think that could be an issue of, let's say, Java and Python, that it's too forgiving at times. So you don't really learn the lessons you need to learn when you start out.
Just a few days ago, I read that idea that people who started with C or C++ are better programmers in any language.
Yeah, I would
think-
tend to agree with this.
I think it depends.
Yeah, there are always exceptions.
Yeah, there are people who then try to write C in Java, which doesn't really work. Or people who fight using classes in Python. It's a bit like if you switch to a different programming language, completely independent what you've used before, if you switch to a different programming language, you have to actually get into it and actually allow yourself to learn.
Yes, and I would encourage people to learn different languages and not be just focused on one single language.
Yes.
To become an expert in that field. It's tempting, but I don't think that's the best way to go about it.
Even if you, in your professional life, decide to be an expert in, let's say, Java, it will help your Java programming when you know other programming languages and learn their concepts. If you're a C++ programmer, learn Rust. It teaches you stuff that you didn't know before. You might not directly apply it to your C++ programming or to your Java programming or whatever, but it teaches you thinking about things. For me, for example, at university, we had Scheme. That was my introduction.
We did as well, yes.
Yeah, that was my introduction to functional programming. And it changed the way that I thought.
As well. Yeah.
Sure. It changed the way that I thought about programming. So I think that.
And just in general, I would say that functional programs tend to be more elegant than, let's say, an imperative language. I mean, this is again a generalization.
Yeah, because have you seen File.io in Haskell?
A long time ago.
It's not really elegant because, it's always, for me, it's always like when you have a language that tries to be pure in one paradigm, then there's always places where they lack, where you have to shoehorn the thing that you're trying to do into that paradigm. That's why I'm such a fan of the multi-paradigm languages like C++, like Python, to a lesser degree Java. Java is very much focused on object orientation.
But they are moving in the direction of functional paradigm as well. You might argue that it's mainly superficial, but there are some important concepts in the later iterations.
Actually, I think a big step for Java was the Streams API, because it moves you towards programming in expressions. You can write relatively complex transformations very clear in an expression.
Yeah.
So I think that was a very good step. But even there, the way you think about building it is object-oriented.
Yeah.
So every container has to include all those functions, etc. Every container class. When you look, for example, at the C++ ranges library, or I found a library for Python called Pipe, which is very similar. There, the implementation of these algorithms can be outside of the class. So, very obvious one is creating a vector from a range. That will be a constructor in the vector class, of course, but doesn't have to be a function of the range class. If you do that the Java way, every range class or every containing class would have a to-vector function.
Yep.
So that's what I meant with Java is still a lot more bound to object-oriented thinking than C++ or Python. And there are other multi-paradigm languages, so I just happen to like those and know those two pretty good.
Yep.
To wrap this up, finally, we would be happy to receive any kind of questions or comments you might have on this topic. You can reach out to us on our social media channels. That is code-is-communication on Facebook and LinkedIn. The same with underscores instead of dashes. So code_is_communication on Instagram. On Blue Sky, it is like our domain name where you also find our podcast directly. So in Blue Sky, it is at code-is-communication.fm. And on Mastodon, it is at cic-podcast@hostsharing.coop. And if you still prefer X, you can find us there as at code_is_com. We also have a mail address, and that is cic@code-is-communication.fm. Okay. Take care, everyone. Bye-bye. Code is communication.